Our topic is linked list. First of all, we will discuss the problems with array. As we know, array is a fixed length. That means when we create an array, it occupies a full block of memory. To expand an array, we have to create a new array that is longer in size, and we have to copy the contents of the older array into a new array. Arrays have a problem of insertion or deletion. If we want to insert a new element, we have to create a space and then we are able to insert a new element. Or we have to create a new array and copy all the elements into a new array. Or if we want to delete an element from any index location, then a blank space is created and we cannot left a blank space in an array, so we have to copy all the elements to cover the space. To solve this problem, we have a solution that we can attach a pointer to each item in the array which points to the next item. This is the linked list. A data item plus its pointer is called a node. A linked list or a one-way list is a linear collection of data elements called nodes, where the linear order is given by means of pointer. What is a linked list? A linked list is a series of connected nodes where each node is a data structure. A linked list can grow or shrink in size as the program runs. If we want to add a new data, we simply add, we simply allocate a new node or insert a new node in a series. If a particular piece of data needs to be removed from a linked list, the program deletes the node containing that data without disturbing the entire list. The linked list consists of nodes where each node contains a data field and a reference list that points to the next node in the list. Each node is divided into two parts. First part contains the information of the element. Here that is represented in data. Data is A, or we can store any type of data according to our data type. Second part is a link field that points to the next field or a next connected node in a list. Here is a representation of a linked list in a memory. First of all, here we have created a representation of array. Array, as we created an array, it reserves a continuous or contiguous memory locations in a memory. But for linked list, we are created node dynamically as per our requirement. We can easily add or remove nodes. When we created a node, nodes are created on any available memory space. First of all, a node A is created, that is head pointer points to the first node. First node have a reference of a next connected node, that is a node B, that is also created on another memory, any available memory space, and node B have a reference of a node C. Here, the head is a special pointer variable which contains the address of a first node of a list. If head is null, that means a list is empty. The left part of each node represents the information part of the node, which may contain an entire record of data. That may be ID, name, marks, age, etc. That is according to the structure of your application or scenario. You have to create a node according to this. The right part represents pointer that is linked to the next node. The next pointer of the last node is null pointer, signals the end of the list. Here it is the representation of a linked list head that points to the first node. If this head is null, that means no list is created. Then this list contains an ID and a name, and this part points to the next created node and a next data is stored, and node B have a link or a reference of a next connected node, and so on, and the last node contains null, and this null means this is the end of list and there is no connected node after this node. Here are the advantages of arrays over linked list. A linked list is appropriate when the number of data elements to be represented in data structure is unpredictable. When we have no idea about how many data elements we want to store in according to our problem, then we have an option that we can use a linked list. It also appropriate when there are frequently insertion or deletion occurred in a list, and the linked lists are dynamic, so the length of a list can increase or decrease as necessary. Here are some disadvantages of a linked list. In a linked list, random access is not allowed. We have to access all the elements sequentially starting from the first node. In a linked list, we have required extra memory space for a pointer with each element of the list. It is not cache friendly since array elements are contiguous location. There is a locality of reference which is not there in case of a linked list. Here we discuss the types of a linked list. Linked list uh, have various types. First of all is a singly linked list. Singly linked list means item navigation is forward only. Means first node have a reference of a next connected node. It does not have any connection with the previous node. In a doubly linked list, items can be navigated forward and backward. In this, in a doubly linked list, each node have information about a previous node as well as a next node. Circular linked list, a last item contains link of the first node as next, and the first element has a link to the last element as a previous node. In this representation, circular linked list, the last node have address of a first node. Now we will discuss about first type, that is a singly linked list. Singly linked list is a type of linked list that is a unidirectional and it can be traversed in only one direction from head to the last node. Linked list is a linear list of specially designed node where each node is divided into two parts. Each node contains data field and a reference field that points to the next node. Info field, it contains the information about the item of the list to be stored and processed, and next field, it contains address of a next node. This field is used to access the next data item in the order. In a singly linked list, uh, it allows insertion and removal of node at any point in a list, but it does not allow random access. As we can easily done in array, we can easily navigate or randomly access any element through index position, but in singly linked list, it is not possible to randomly access each element. We have to traverse sequentially to find the required element. Any node in a list can be accessed only by the starting from the first node sequentially. Here are the some operations that we can perform on a singly linked list. First of all is insertion. And that means we can add an element at the beginning of the list, or we can add an element at the end of a list or at any position. Same as deletion, we can delete an element from the beginning of a list as well as we can delete an element from end and from the specified position. Display means we can display a complete list or all the elements that we have stored in a list. Search means that we can search any element from the list. We can implement a list using array and structures. Now we will discuss a few algorithms or operations that we can perform on a single linked list. First of all is traversing a linked list. How we can traverse a linked list? This operation is used to visit each one of the list exactly once in order to access the info stored in nodes. It uses a pointer variable which points to the node that is currently being processed. So, a link pointer is used that points to the next node to be processed. Thus, a pointer that is assigned a link pointer, it moves the pointer to the next node in a list. This is our algorithm for the traversing in a singly linked list. If start is equals to null, start or a head, we can say it also a start. If start is null, that means list is empty or our procedure is stopped here. Otherwise, we set a pointer is equals to start. We have taken a special pointer and we assign this pointer address of start or a head. That means this pointer points to the first node. That is the address of first node is 23145. This pointer points to the first node. Repeat step 4 and 5 until pointer is not equals to null. If this condition is true, pointer is not equals to null. Here we have an address of a first node. Condition is true. Then it comes to the body of a loop and we are accessing and applying pointer is equals to info. We are accessing this information of a first node, that is the name of a person. Now here we are assigning pointer is equals to pointer next. Here we assign the address of a next node. Pointer is pointing to this node and we have this address. This address will assign to the pointer. Pointer will now points to the next node. Again, check. We have to check the condition, that is pointer is not equals to null. Yes, condition is true. Now we have now we can access the data of a next node, that is the name of a second person. Again, we are going to assign pointer is equals to pointer next, means this address is now going to assign pointer. Now pointer will assign the next node. Again we check the condition that pointer is not equals to null. Condition is true. We are now again assess and apply pointer info. In this step we can print the information or we can apply any other operation, for example searching operation, to search our data. Again here we assign pointer is equals to pointer next. This address will assign to the pointer and the pointer will now point to this node. Here we again check pointer is not equals to null. Yes, condition is true and we now again assess the information of this node, that is the name of this person. Again we assign the assign pointer is equals to pointer next. That means this null is now assigned to the pointer. Now again check the condition, pointer is not equals to null. Yes, pointer is now equals to null. The procedure will stop here and loop is, and the whole list is now traversed, and all the data elements are checked, or whatever the operation we have applied here is now completed. Here, how we can search in a linked list. In searching, we traverse the list as we have done the procedure previously. We traverse the list from beginning and compare the elements stored in each node with the desired element to be searched. If match is found, then the address of node is returned, otherwise we proceed to the next node. If element is not found till null, then search is unsuccessful. Start with the start is equals to null. If start is null, then linked list is empty. Otherwise, we will assign pointer is equals to head, or a we can call it as a start. As we have performed our traversing procedure previously, in this algorithm, we just added a conditional statement that compares the required information with the information part of the node. While pointer is not equals to null, this procedure will traverse the whole node until the pointer is not equals to null. If this condition is true, it comes to the body of the loop and it checks the condition. If pointer info is data, this is a comparison statement, and it checks the required data that we want to search with the pointer information part, uh, where the pointer points the node. If element is found, it will return the pointer or the address of that particular node and exit. Else, if the data element is not found or this comparison is not successful, then it comes to the else part and it assign the address of a next node to the pointer, and the loop will end if the search is unsuccessful or no element is found. This statement will be printed element not found in a linked list. We can also perform insertion and a deletion in a linked list. Before performing insertion and deletion, we have to create a node. To create a linked list in a memory, use structure, which is a self-referential structure. Self-referential means one of the member of the structure is a pointer that points to the structure itself. This is the code of how you can create a node. Struct node, and here we mention our data members as our requirement. Int data, we have only one data item. We can add as per our requirement and mention data types, like if we want to store the name of a person or CNIC or a phone number, then we have to mention the data type according to our problem. Here we have only one data, that is integer type int data, and this is a self-referential data member that points to the structure itself, and this is a node link. Creation and insertion of a data in a node. This part will represent that we do not have any list in our memory and we have to create our first node. Struct node height is equals to null. We have created a new node, means currently the situation is that head is equals to null. This is a head or a start, and we do not have any list created in our memory, and this head or a start is currently null, and we are going to create our first node. How we can create our first node? Here head is equals to null. We are going to create a new dynamic memory. Head is equals to new struct node. This head will now assign a new dynamic memory allocation that is according to our structure data members, that is a data and a link. Head data is equals to data. Here we can insert our data. Data can be of any value or any name according to our specified data type. Here we assign head link is equals to null because this is our first node. That's why we assign link null, because there is no any other node after this node in this current situation. Our first node is created. Insertion of a node into a linked list requires a free node in which the information can be inserted, and then the node can be inserted into a linked list. We can insert a node before header or at a beginning or at the end of a list or at the specified position. Before insertion or a deletion, we have to check overflow and underflow conditions. Overflow happens at the time of insertion. If we have to insert new data into a data structure, but there is no free space, that is availability list is empty, then the situation is called overflow. Overflow will occur with our linked list when avail is equals to null and there is an insertion operation is to be performed. Underflow is referred to the situation when one wants to delete data from a data structure that is empty. The situation is handled by printing the message underflow. Observe that underflow will occur when our linked list when start is equals to null and there is a deletion operation to be performed. This is insertion at a beginning, means that we have to insert this new node at the start at the beginning of our first node. This is the procedure how you can insert a new node at a beginning. First of all, we have to create a pointer, that is temp. Here we are going to assign a new dynamic memory allocation. You can use a malloc method or a new method to dynamically allocate a memory according to the size of a struct node. This new dynamic memory memory is held by a temp pointer. Temp info is equals to data. When we are going to create a new node, first we have to fill up the data part. Then temp link is equals to start. Now we going to assign a temp link, that is a new node that is we have currently created and working on it. We will assign the link of us. We will assign start to the temp link. Start is equals to temp, and here we will assign the address of a temp to the start. Let's check the working of this algorithm. This is a new node that is held by a temp. Suppose the address of this node is 100. That is a newly created node. and the address of newly created node is 100, and the address of existing node is 200. This is the first node, and head points to this first node. According to this instruction, temp points to the new memory allocation. Means this is a temp and temp points to this memory allocation. Now temp info is equals to data. Here we fill the data, that is 20. Temp link is equals to start. Here this is a temp link, and we are going to assign the address of a start or head to a temp, that is 200. So this link is created. Okay, this link is created. Next statement is start is equals to temp. Head, currently head points to this node. Now we will assign head is equals to 100. Now the link of head points to this new node instead of this first node. This link is now breaked. A new node is inserted at the beginning of a list. Now, how you can insert a node at the end of list? To insert a node at the end of a list, we have required two pointers. First is P, that is used to traverse and to find the end of a list, and temp is a pointer that holds a new dynamic memory allocation. Temp is equals to struct node and malloc. This is here we have created a new dynamic memory allocation, and new dynamic memory is assigned to this temp pointer. This temp pointer holds this new memory. Here we fill the information part of a newly created node. Temp info is equals to data. Now we will assign P is equals to start. P points to this node, while P link is not equals to null. This will traverse or uh, continue our loop until P link is not equals to null. The pointer will move to the next node until this condition is not met. P link is not equals to null, condition is true, so we will assign P is equals to P link. This link will be assigned to the P, and now P will points to the next node. If this condition is gets true, control moves to this statement, and here we are going to adjust our new node at the end of a list. P link is equals to temp, and temp link is equals to null. Temp link is equals to null because this is now the last node of our list. Last operation, that is insertion at a specified position. If we want to insert a new node at a specified position, we have to search position in a list. Then we can insert the node after the position. Let the address of the specified node be kept in a pointer. Adjust the pointer so that next pointer of the specified node points to the pointer. The next pointer of the specified node will point to the next pointer of a node pointed by the new pointer. This is the uh, representation of a singly linked list insertion at a specified position. This is a temp that points to this node, and this is a new node. The statement will work as pointer next is equals to temp next. This is a pointer next, and this pointer next will assign a temp next. The address that is mentioned here is now assigned here. Temp next is equals to ptr. The address of this node is assigned this, so the link of a new node is created at a specified position.